Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Let's continue from where we left in the last class. We'll cover some more essential physical metallurgy concepts in this class. The types of solid phases, chemical order, components, chemical composition units and types, and phase fractions. So very important ideas to understand this course better. Let's see what are solid phases. Let's start with the simplest of the phases, pure element. A pure element, for example, pure nickel. Here it has a crystal structure and a chemical composition. Crystal structure is FCC. This you can see this as a two-dimensional representation of a FCC unit cell, FCC crystal structure, where you can see one particular unit cell phase here. The corners are having atoms and the phase center has an atom. So this is a repetition of the same in a two-dimensional plane. So this is an FCC crystal structure, and the composition is 100% nickel. So this is simple to understand. Let us think about solid solutions where two or more elements come together. Example 1 is copper dissolved in nickel. Let's think about the same nickel pure element where some of the locations are not nickel anymore. So these two are copper atoms now. They are sitting in the position of nickel now. So this is a nickel copper solution. So the structure is obviously FCC. It has not changed. And the chemical composition is now changed. Some copper has occupied the nickel position. Therefore, we have to say chemical composition is in some percentage of copper. So here we are saying 0 to 100%. So when we say chemical composition of copper is 0 to 100%, it means copper can be 1%, 10%, 50%, 80% and even up to 100%. So you can imagine these gray atoms replacing nickel atoms, the white atoms, all the way up to a complete replacement. So that's the meaning of 0 to 100%. This is some special case where we call them isomorphous solutions. In those solutions, this kind of complete solid solubility happens. The second example is carbon dissolved in iron. So you can imagine iron atoms like FCC unit cell, like FCC crystal structure, all white atoms are Fe, and in between them, the atoms are sitting. Okay, they are actually not replacing the iron atoms, they are sitting in the gaps between iron atoms. So the crystal structure is FCC, chemical composition is 0 to 7% copper. Okay. So the percentages here are atomic percentages, mass percentage. We will come to that later. So solute atoms occur among solvent atoms. This is how a solution is. And crystal structure type of solvent does not change. So here it is FCC crystal structure for the nickel, and as copper dissolves, that structure doesn't change. Here it is FCC iron crystal structure and it doesn't change as carbon dissolves, right? But there are interesting questions one can ask. If copper is 50% in this first case, which one is solute and which is solvent? So even in a binary two element system, when we have two elements mixing completely into each other, this sort of problems can come. So having this notion of solute solvent is convenient in many situations, but not everywhere. Okay, but what is important is there are two elements which are completely dissolving in each other. That is more important. So solid solution is elements mixing or dissolving in each other in this manner. There are two types of solutions. One is substitutional solid solutions. Solvent atoms are in their lattice positions and solute atoms replace them and occupy the lattice positions. Whereas in the interstitial solid solution, we have solvent atoms in their lattice position. The solute atoms occupy the spaces between them but do not replace them. Right, that's about the solid solutions. Now one more important type of solid phases, compounds or intermetallic phases. So in the chemistry that you might have studied till now, you might have come across several compounds, NaCl, methane and so on. Okay, so those are all compounds. So when it comes to metallic systems, we have these intermetallic phases. Intermetallic phases have predominantly two types. One is stoichiometric phases, which have fixed composition, also known as line compounds. Example Fe3C. So it has a crystal structure of orthorhombic and chemical composition of 25% carbon. The second type is non-stoichiometric phases, which do not have a fixed composition. There is a range of composition. Okay. For example, AlNi compound. So you may think AlNi, seeing this formula, aluminum is 50%, nickel is 50%, just like NaCl and all. But this is not so. Here there is a range of solubility possible. Nickel can vary all the way from 45 to 60%. So this is where this is non-stoichiometric in nature. Okay. So the other names for these intermetallic phases are intermediate phases, intermetallic compounds, and even intermetallics. So there are different names: intermediate phases, intermetallic compounds, intermetallics. So in different places, different names are used. But these two major types are good, like on stoichiometric phases and non-stoichiometric phases, fixed composition and a range of composition. Okay. So what is common to all these things is they all have long-range chemical order. Okay. So what is long-range chemical order? So compounds and intermetallic phases have long-range chemical order. Sometimes it is called as long-range order. I feel this is kind of misleading, because in metallic glasses, people who work on metallic glasses, for them crystalline order is more important. A small pocket of crystallinity can come within the metallic glass. So they would like to call it as order. Okay. Here we are very sure that it's a chemical order, and crystalline order is already there in these phases. So this word long-range order actually refers to long-range chemical order. For example, in AlNi phase, crystal structure is it looks like a BCC, but it is not. It's called as B2. It's a structured baric notation. That is the common name used for this. And aluminum prefers body center and nickel prefers body corner. That is, the chemical elements aluminum and nickel do not arrange randomly. They show a clear preference to a type of lattice site. Okay, we can understand this better by imagining them like this. Let's say nickel atoms being a simple cube and aluminum atoms being a simple cube interpenetrated into each other. So in this way, if you imagine, the aluminum goes into the body center of the first simple cube, the nickel simple cube. Okay, this looks like a BCC, but it is not. It is basically two simple cubes interpenetrated. All right. So these are two simple cubes interpenetrated. The nearest neighbor of an aluminum is nickel, and for nickel it is aluminum, right? Like this in the 2 dimension. You can see all red atoms are surrounded by gray atoms. They are touched by gray atoms. Okay. So in that way, there is a clear preference for the neighbors. Aluminum prefers nickel as the neighbor, nickel prefers aluminum as the neighbor. But imagine in the position of aluminum, one nickel atom comes. Then there is a nickel-nickel bond which is forced, right? That is less preferred compared to nickel-aluminum bond in this kind of phases. So this particular repetition of AB type of atoms, in this case, is a long-range chemical order. Okay, this is where we say chemical order occurs. So this is fundamentally different from solid solutions. So if you see in solid solutions, we have solute atoms and solvent atoms. All of them are sitting in FCC structure, all right, but they don't prefer a particular site, a body phase center or phase corner, doesn't matter. Nickel can go anywhere, copper can also go anywhere. So solid solution is a type of phase with no chemical order. So atoms have random mixing. So in substitutional solid solution, solvent atoms and solute atoms can exchange their positions in their lattice. Example, copper can go into nickel position and vice versa. So in interstitial solid solutions, the carbon atoms that are here in between iron atoms, they can change their position to any similar interstitial site. So that is the randomness there. So this randomness is not in crystallinity. Okay, the atoms arrange in crystalline order anyway, but the chemical elements arrange randomly. They do not show any preference to a particular site. So this is what a random solution is. Okay, this is fundamentally different from a chemically ordered phase. So let's summarize our understanding. Solid phases have crystalline order. Solid solutions are chemically disordered. Two types of solid solutions are there, substitutional and interstitial. And the compounds or intermetallic phases are chemically ordered. They have long range chemical order. Again, there are two types. One is stoichiometric, the other one is non-stoichiometric. You can take up a small test for your understanding now. So let's say nickel and aluminum, they have FCC crystal structure. And the first question is, nickel can dissolve about 10% of aluminum at 1000 degrees Celsius to form a solid solution in FCC structure. So the maximum solubility of aluminum is now 10% in this case. So does this solution have chemical order? That is the first question. Second, same nickel and aluminum form an intermetallic phase with a different structure, that is the L12 crystal structure, and Al3Na is the stoichiometry of this intermetallic phase. So in this case, is there a chemical order? Okay, so pause and think about it. Once you are ready with the answer, you can play and see what is the answer. Okay, fine. Let's understand one more important idea. Components. We have used this word already. Let us see what is it. What is a component? Chemically distinct substance. Depending on the context of the study, the components are selected. For example, formation of H2O from its elements. This is the context. Then what are the components? Hydrogen and oxygen are the components. So here if we want to talk about composition, we represent it in terms of percentage of hydrogen. That is percentage of one component. Okay, so hydrogen is the component here. So when it comes to solution of sugar and water, mixing 1 spoon of sugar in water and dissolving it. Now this is the context of the study. The context is now changed. It's not formation of a compound anymore. It is dissolution of one substance to the other. So these substances, sugar and water, they are the components now. So in that way, composition of this solution is represented in terms of percentage of one of these components, that is sugar in this case, 69% of sugar, percentage of one component. See, so the component is selected based on the context of the study. That is important. So based on these components, the material systems are classified. If we have only one component in a system, it's called as a unary system. If the number of components are 2, it is binary, then ternary, quaternary, quinary, and so on. We will be using these words as we go along. We have one question now. The context of the study is H2O changes from liquid to vapor phase. Is it one component or more than one component, and what are they? That is the question. The second question, aluminum and nickel form Al3Na phase. It's a different intermetallic phase. Okay. So in this case, so how many components are there and what are the components? Pause, think about it, and then play, see the answer. For the first case, it is one component H2O. For the second case, it's two components aluminum and nickel. I hope you got it right. So let's see about this, one of the most important ideas of this course, that is composition. So chemical composition is the content of components in terms of percentages or in terms of fractions. The sum of percentages of all components must be equal to 100 and sum of fractions of all components must be equal to 1. Let's consider a AB system. Units are mass percentage of A that is the first unit we are going to consider, or weight percent of A. Mass and weight are interchangeably used. Mass of component A divided by total mass multiplied by 100, that is the mass percentage of A. Quite simple. Atomic percentage of A is number of atoms of component A divided by the total number of atoms multiplied by 100. So this is also quite straightforward. Mole percent may be slightly tricky. It is number of moles of component A divided by the total number of moles multiplied by 100. Let's look at this mole percent in more detail. So what is a mole? It's nothing but a number. It's Avogadro number 6.022 to 10 power 23. So that is the number. Why is it important? It's extremely convenient. You see, if you take, let's say, about 56 grams of iron in your hand, something that you can practically sense, 56 grams of iron. What is that? It is there in the periodic table. When you see the atomic number and atomic weight is written in the periodic table. For iron it is 26 atomic number and about 56 atomic mass. This atomic mass is in gram mole, or it is in gram per mole. 1 mole of atoms will weigh this much. So how many atoms are there in your hand now when iron content is 56 grams? It is 1 Avogadro number of atoms, 6.022 to 10 power 23, 1 followed by 23 zeros. That many number of atoms are there in your hand now. Okay, so that's, you can imagine how small the atom is from this, right? So the atomic mass is nothing but the mass of 1 Avogadro number of atoms or 1 mole of atoms. Okay, so instead of saying every time 10 power 23 atoms, we can say 1 mole of atoms. So it's merely counting. Okay, if we say multiple number of moles, you have to imagine how many number of atoms are there, right? So yeah, but mole is used in a slightly more versatile manner. It is used also for molecules. That is where the problems come. When components are only elements and not compounds, molecules, the mole fraction and atomic fraction are the same. Okay, so let's see it in more detail. For example, consider H2O. Hydrogen and oxygen are 2 elements. And they are the components now. Okay, when we, let's say, consider formation of H2O and things like that, the components are going to be hydrogen and oxygen. Then we can say 67 mole percent is present in this compound. It is the percentage of hydrogen atoms. Now we are saying atoms, so therefore the mole percent and atom percent are same here. Okay, 67 mole percent of hydrogen or 67 atomic percent of hydrogen are both same. Let's consider another case, a solution of 5 moles of sugar mixed in 95 moles of water. So the context is different, therefore the components are going to be different. Water and sugar, these are now molecules, right? H2O molecule, C2H22O11 molecule. Those are the components now. So 95 mole percent of water is present. That is how we express the composition now. It is the percentage of water molecules and not atomic percent. Okay, because atomic percent is only used for atoms such as hydrogen and oxygen and not for the compound H2O. Okay, so the mole percent is not same as atomic percent here when component is a molecule and not element. Okay, not atom. So how to convert from mole percent to weight percent is an important thing. Let us see one example quickly for that. Let's say 25 mole percent carbon, convert that into mass percent. So atomic mass of carbon is the important data here and atomic mass of iron. Okay, so mass percent of carbon now is going to be 12.011, the carbon's atomic weight multiplied by atomic percentage 25, and in the denominator also we have both carbon and iron's atomic weights and their atomic percentages. So what we are essentially doing is taking mass of carbon in the numerator and mass of carbon plus iron in the denominator. So we get 6.67 mass percent or weight percent. In this course, we will be using this unit mole fraction more. So let us look at it little more in detail. So consider a pure element A. There are 30 atoms, all are A atoms. What is the mole fraction of A now? The symbol that will be used for mole fraction will be X. So X subscript A is mole fraction of A. It's equal to number of atoms of A divided by the total number of atoms. So it's going to be 30 by 30 here, which is 1, straightforward. Now think about a AB solution where we have 30 atoms in total, but 24 of them are A and 6 of them are B now. So in this case, what is the mole fraction of A? It is 24 by 30, 0.8. And automatically the XB is going to be 0.2. But if you think about what is this mole fraction carefully, you will realize that if we have this XA of 0.8, what does it mean? If we have 30 atoms, 24 are A in that. Or if we have 5 atoms, 4 are A in that. So if you have 1 atom, 0.8 of that is A. So mole fraction is actually a probability. You see, the total is going to be 1, right? In that, how much is A? That's the question we are asking. So this is essentially a probability. XA is probability of a lattice site to be occupied by A atom. There is 80% of chance for a particular site to be A in this solution where we have 24 A and 6 B atoms. Okay, so mole fraction can be understood as a probability. So this sort of understanding is also important as we go along. Let's consider some hypothetical cases of pure elements and phases and understand overall composition and individual phase compositions. So let's imagine the phase equilibria. This is now a single phase. The XA1 is overall composition, and composition of phase is also going to be the same because it's only a single phase. So the overall composition and phase composition are same in this case. So if you consider one more element B, 30 atoms of all B, what is the mole fraction of A there? It is 0. If we consider a phase alpha, which is a AB solution, in that there are 60 atoms now, 30 of them are A and 30 are B. The overall composition in this case is going to be 0.5 mole fraction of A. Because it is only single phase, overall composition and phase composition are same in this case also. So composition of alpha phase is going to be also the same. Now let's consider a two-phase scenario. A and B together form two phases. One is the solution alpha, the other one is a compound which is eta. It's a A3B kind of compound. Overall, we have 60 atoms, 30 of them are A and 30 are B. Now the overall composition we can calculate as 0.5, but the individual phase compositions are going to be different. The alpha phase has 46 atoms, 18 of them are A, 26 of them are B. Therefore, composition of alpha phase in terms of mole fraction of A is going to be 0.39, and for eta phase it is going to be 0.75. This is another example. It's a copper chromium alloy where the overall composition is 50% of chromium. And the individual phase compositions, the light gray phase here has 1% of chromium in that, meaning the 99% is copper. Dark gray phase composition is 99.9% chromium, almost pure chromium, which has only 0.1% of copper. Okay? So this is the overall composition and individual phase compositions in this case. Okay? So now that we are comfortable about overall and individual phase compositions, there is one more related idea to the microstructure, which is phase fraction. Let us look at that. If we have two phases, what is the individual phase fraction? Overall 60 atoms are there, and alpha phase has 46 atoms, eta phase has 16 atoms in total. Therefore, when we talk about phase fraction of alpha phase, we can use 46 by 60 and say 0.73 is the mole fraction of alpha phase, and the phase fraction of eta phase is 16 by 60, which is 0.27. So this is how we calculate mole fraction of phases, but mole fraction is not that frequently used unit for phase fraction. It is the volume fraction. So let us how it is calculated or measured. You can see this is a micrograph here. Light gray and dark gray phases are visible, and area fraction in the image can be calculated. Light gray phase is about 0.6 and dark gray phase is about 0.4. So in this image 60% is light gray, 40% is dark gray. So from this area fraction we can convert this into a volume fraction as well, and we, if possible, mass fraction and mole fraction can also be used as units for phase fraction. Alright, so the word phase equilibria, which we have already seen, if I bring it here and recall what we have and recall the different hypothetical cases that we have seen, we can say that this pure A or the alpha AB solution, these are all single phase equilibrium. Only one pure A is there or one solution is there in the entire system. That is called single phase equilibrium. And if we have alpha and eta or this light gray, dark gray, chromium rich phase and copper rich phases, we call that two phase equilibrium. So like this, even multi-phase equilibria is possible. So all these terms that we have understood in this class will be useful for us to understand the reasons behind the phase equilibria and use them to predict microstructure. So with this we will stop. I hope the lecture is useful. Let's see in the next class.